Hello and welcome to the IDS Vision Channel. My name is Boris Duché. I am the product manager in charge of the Encenso 3D camera product line here at IDS, and I will hold today's presentation full-featured 360-degree point cloud using a multi-camera setup. I will start with the basics for understanding 3D imaging, explain briefly what makes the Encenso product unique, teach you how to set up a multi-camera system, and finally highlight what makes our latest release, the Encenso B, complementary to our existing portfolio. Let's start with the basics, trying to understand what we call 3D data in opposition with 2D images coming from conventional monocular camera. In a 2D color image, each pixel is encoded with three values corresponding to the red, the green, and the blue channels. These values will typically range from 0 to 255 for an image that is encoded in 8 bits mode. At the monitor level, each pixel is made of 3 LEDs. One is red, one is green, and the latest is blue. The intensity of each LED will be adjusted according to the pixel values encoded in the image. As a conclusion, you can say that a 2D color image contains 3D information for each pixel. Only this 3D information is in the RGB color space, where when talking about 3D cameras, we are looking for depth information. A depth or a 3D camera will typically output a depth map. This is a 2D image where each pixel is encoded with three values, a X, Y, Z triplet in millimeter that contains the position of the pixel imaged by the camera in a given Cartesian coordinate system. It is common practice to display these depth maps with a color scale. In this example, the greenish pixels correspond to the information close to the camera, while the bluish pixels correspond to the information far away from the camera. Note that you can end up working with a color 3D camera. In that case, each pixel will be encoded with the XYZ triplet, given the position of the pixel in space, plus the red, green, and blue information. In that case, you have a 6-dimension information per pixel. Of course, it is possible to compute a point cloud out of this depth information. In this example, here is what a point cloud look like. Those are two different ways to show the same information. Each pixel contains the localization of the information in space. But computing a point cloud takes time and resources. You need a GPU. So sometimes some algorithms, they require that you compute the point cloud, typically in a 3D matching algorithm that you will use for a pick and place application. You will need to compute the point cloud, but it is not always necessary. Presence absence detection, you don't need to compute a point cloud and you can save GPU resources. Now let's take a deeper look on the Encenso technology. How does it work? What makes it unique? So the Encenso technology is based on stereo vision. The principle is similar to the human eyes. When looking at an object, this object will be imaged on both retinas. And based on these two retina images, your brain will deduce depth information. Now looking at the Encenso B. And ignoring the central element of the device for now, the objects that we look at will be imaged on both sensors. Both images will be sent to the computer that the camera is connected to, and the driver of the camera will be responsible to compute the depth information. Let's take a look at a concrete example to understand how it works. So we have a scene in here observed from two different points of view. So the image that you can see correspond to the image at the sensor level from the left and right sensors of the Encenso B camera. And the algorithm will try to find, for each pixel of the first sensor, the corresponding pixel in the second sensor. If it succeeds, the depth information will be properly computed. It usually works good on areas with local contrast. In this example, looking at the drawings on the cup, you can see and easily distinguish a pixel from another. I have in here a pixel that is black, the pixel underneath will be white maybe, and the surrounding pixels will have specific gray levels. Can I find the corresponding pixel on the second image? Yes, I can, because this pixel together with its surroundings is very unique. Problem comes when you look at homogeneous areas. Let's take a look at the foreground, for example. We have white pixel, white area in here. I have a white pixel surrounded by white pixels. I'm looking for the corresponding pixel on the second image. And how many candidates I have? So many. I have actually all this area in here. So most certainly, my matching algorithm will fail and will produce an incomplete depth map. So working with conventional stereo vision system, you will face a weakness on homogeneous surfaces and compute incomplete depth maps. So how did Ensensor overcome this issue? The trick is actually pretty simple. We use a pattern projector. This is a unit inside the camera that is only responsible to add contrast to the scene, helping the matching algorithm to distinguish from one pixel to the other. Let's take a look at the same example than before, but now with the pattern projector. Now we see the same scene, but with the random pattern that is projected. Each pixel looked out together with its neighborhood is very unique. There is no more homogeneous areas in my images. The stereo matching algorithm will hopefully be more successful, and the depth maps that will be computed will be more complete. Yet, you can see that some areas are still missing. In that case, the shadow areas. So on the right image, you can see the shadow of the cup on the right, and on the left image, you can see the shadow of the cup on the left. I computed this depth map myself via PowerPoint, so it's not perfect, but the idea is to show you that the shadow areas that you can see on the right image are not located in the same place than the shadow areas that you can see on the left image, making it impossible for the matching algorithm to find the corresponding pixel from one image to the other and building incomplete depth information. Actually, there is an easy way to overcome this issue. This is to work with multiple cameras. So the multi-camera setup, how does it work? Because the projected pattern that we have on a sensor camera is only there to add contrast to the scene, and in opposition with fringe projected techniques that are widely used by 3D camera manufacturers, one can use multiple Ensensor cameras with overlapping fields of view to produce a full-featured 360 degrees point cloud. Let's take a look at the example I used to make these screenshots. I used in this example two cameras. One is making an acquisition of the scene from the front, and the second camera is making an acquisition of the same scene from the back. Just going through a very simple process of calibration, I can merge directly these 2 point clouds together and produce the fully featured 360 degrees point cloud. It only requires a calibration step that I will explain in my next slides. So how do we achieve that? It's very easy. You will just need to place a calibration target onto the scene, visible by both cameras, to calibrate your system. This calibration plate will be used to define the origin of the coordinate system. All 3D acquisitions that you will make with your multiple cameras can then be merged directly because they share the same coordinate system. It's useful to understand that from a software point of view, using multiple cameras looking at the scene from different angles of view, or using a single camera that you will move around the scene, typically mounting the camera onto a robot, or using a single static camera but moving the scene in front of the camera, all of this is exactly the same from software point of view. You just need to calibrate your system, and then you can merge all the 3D point clouds that share the same coordinate system together. Before we start the demonstration, how to use multiple 3D cameras, multiple Nsenso 3D cameras, I would like to highlight what makes the Nsenso B complementary to our existing Nsenso portfolio. So the Nsenso B completes the Nsenso C lineups. The Nsenso C was introduced a year ago, and those come with 3 baseline options: small, medium, and large, to choose depending on your working volume and your operating distance usually. This Nsenso C comes with 5 megapixel monochrome sensor plus an integrated RGB module. The idea being to map the RGB information onto the 3D data. The Nsenso B is much more compact. It is available with 2 5 megapixel color sensors or mono sensors. You can choose, but there is not an additional RGB module. So you can choose to have the camera with color sensors, and then you will have natively colored 3D point cloud, or you can choose to have the Nsenso B with monochrome sensors. You will lose the color information, of course, but you will increase the spatial resolution. Another key difference with the Nsenso B is that it is focused at the close range. It is focused at 350 millimeters. That makes it optimum for operation at a short range. As a comparison, the Nsenso C with the smallest baseline is focused at 950 millimeters. So the Nsenso B can be used for pin picking application of very small and very complex parts, or it can be used mounted on a robot to go quite close to the scene and achieve high data accuracy. You understood you have 2 options when you buy an Nsenso B. You can buy the color version that comes natively with color sensors, or you can buy the monochrome version. The color version of the Nsenso B comes with a green projector. The Quantum Efficiency Curve, QE, is a sensor information that gives you the pixel sensitivity to a particular wavelength. So higher the better. As you can see on this graph, the IMX568 that we use in this camera is more sensitive to green. This is quite common with color sensors. The green projector permits to achieve high contrast imaging within a short exposure time, thus increasing the maximum frame rate that we can reach with this camera. Now, if you choose to work with the monochrome version of the Nsenso B, it will come with a blue projector. Monochrome sensors, in that case, you can see the quantum efficiency curve of the IMX568 mono version. The mono sensors is more sensitive to the blue light. This is why you will find a blue projector. This is what you find on the other Nsenso cameras, because Nsenso cameras, until the Nsenso B, always came with monochrome sensors for the stereo matching. Now, just before we go to the demonstration, where you will understand what makes the Nsenso B unique and how to achieve full-featured 360 degrees point cloud, quick recap what makes the Nsenso B unique. Best data quality ever. Because the Nsenso B comes with 5 megapixel sensors and is optimized for the close working range, you can achieve unmatched data quality. I would like to show you an example of the first 3D acquisition I made with my first prototype of Nsenso B. So when I received the camera for the first time, what I did is just to put my hand in front of the camera and make a 3D acquisition. That's my end. It covers roughly a third of the field of view of the camera, and it is 20-30 centimeters away from the camera. And what I want to show you, first 3D point cloud I made with this camera, I could get my fingerprints on the point cloud, which is amazing. Amazing spatial resolution, amazing data quality. Of course, this is possible to achieve that accuracy with the monochrome sensor version of the camera. If you choose to work with the color version of the camera, it is the same in 3D and in 2D. If you choose the color version, yes, you have the color, but you lose some spatial resolution. That is another topic we will not cover today. So best data quality is the first reason why you should choose the NSenso B. NSenso B offers you the option or not to have color information. You sometimes need the color information, sometimes not. If you do not need it, always choose the monochrome version. It is the same with 2D imaging because it will permit to achieve a higher spatial resolution. And if you need the color information, you will have natively a 3D point cloud, which means not with like with the NSenso C, where we overlap the RGB information to the point cloud. In that case, natively, the point cloud will be in color. That comes with a cost, the loss of spatial resolution. But in the case of the NSenso B, because the data quality is very good at this close working range, usually that is enough. You have the choice. And last but not least, NSenso offers hundreds of camera variants. If you compare to our competitors, you will mostly find manufacturers that have between 8 and 10 cameras in their portfolio. We have hundreds camera variants, and each of them is optimized for a working distance and a working volume that permits us to achieve the higher data accuracy. So all of these camera variants are compatible. They are operated via the same SDK, and they can be used simultaneously with overlapping fields of view. Because you understood, I hope, that having the pattern projected by one camera overlapping with the pattern projected by a second camera is not a problem. We just want to add contrast to the scene. It can be confusing to find the proper NSenso configuration in our portfolio because we have so many candidates. So in that case, I recommend that you get in touch with your IDS sales contact or your local IDS distributor to find the optimum configuration for your use case. Thank you very much. I will now hand over to my colleague Ute that will make you a presentation, a demo, how to use multiple NSenso cameras in the same configuration. Thank you.
Thank you, Boris. Now let's have a look what we have set up here. We have an NSenso B and an NSenso C camera, and I've opened them already in NXView. Here is the NSenso C and the NSenso B. And as Boris mentioned, it's now about to calibrate the both cameras together. And calibrating here means to compute the transformation from the NSenso B's coordinate system to the NSenso C coordinate system that the software can put the output of both cameras into a common coordinate system. And the result is what you can see here for the color. And so the color camera from the NSenso C, you see here, it's linked to the stereo camera of the NSenso C. And what we now want to achieve is a link between the stereo camera of the NSenso C here and the stereo camera of the NSenso B. So it's only a stereo camera. Okay, let's select the both stereo cameras. I use the control button and click them, and then I open them in the calibration wizard. Now we can choose if we want to calibrate the intrinsics of one of the both cameras, but since they are okay, I skip that. And we choose which camera should be the reference coordinate system. So one of the both is the origin that is used to as the origin for the 3D data for both cameras then. So I choose the Encenso B. And now the cameras are opening, and I can select how to trigger them, and in this case we want to use a software trigger, and I choose software, and now we're in the calibration wizard. We start the calibration procedure by clicking to calibration only and pattern front facing away from us. Now you see here, this is the Encenso B. You see the view of the Encenso B, and this is the Encenso C. And what I will do now is moving the calibration target to get some angled views for the cameras. This improves the quality of calibration. So just let me move to the setup and start with it. So I tilt it in any direction. And there is sometimes a warning that the pattern is moving, so hold it still until the warning disappears. And the counter counts. So this should be enough, and then I click to next step, and this will compute the link between the both camera coordinate systems. So now we check the results. You can check the calibration of the intrinsics as well, it's displayed, and you can see the result of the link calibration, and I will show you on my screen. So this is the Encenso B. You see here the calibration target, and here is the intrinsic error of the intrinsic calibration. This means how the optics is modeled with the calibration data. And as long as this is with a green background, it's okay. And here, so both, this is the Encenso C and B, both intrinsic are okay. And this is the link. And this means the difference between the both views is maximum. The maximum error is here. It's 0.5 millimeters, and the average error is here. So, and this we can save to the EEPROM of the cameras. And with next step, the calibration wizard is closed. And now we can see here that the Encenso C has a link to the serial number of the Encenso B. We choose this camera to be the reference system. So this C is linked to the B model. And now we open them. We can just click on Control A to select all and open them. Now I stop the live acquisition and show you what we have. So here you can select, this is what the Encenso B sees, and this is what the C sees. And this is the interesting part. I show you in full screen mode. So what I zoom in here, you see the coordinate system. We choose the Encenso B. This is this model here to be the reference coordinate system, and you have here the blue line is the Z-axis and the green is the Y-axis. And the blue boxes here, I try to rotate it, but it's difficult. Okay, like this. here you see the viewing field of the Ensensor C. This is this one. And this is the viewing field of the Ensensor B. And now I show you what the software did with the cameras. So I open NX3 Edit, and in NX3 Edit you can see all the parameters that are used to control the cameras. So let's have a look. This is the Ensensor C. We have here the link node, and you see here that the camera is linked to the serial number of the Ensensor B. And if we scroll down, close this camera, this is the color camera. Here you see the link that I showed you in the beginning in the camera list. Color camera is linked to the stereo camera. And now we have the Ensensor B. And here you see that the link is empty. It's not linked to something. And this we can use for another feature. So maybe you don't want to have the object in the coordinate system of that camera, but you want to have it in another coordinate system. And so you can store in the link node of the Ensensor B another transformation. So I go to workspace calibration and want to set the coordinate system for the combined point cloud in the middle of that calibration target. So I just select here the camera I want to use for storing the workspace calibration. And I start it, select workspace calibration, and set origin with calibration target. Then I go to start here. Storing link, that's fine. Let's check. So we have here a link transformation for our workspace. And go back to depths if you want to have 3D data. Now you see that reference coordinate system has moved to the table. And now I can place my object. I brought this, it's a concrete piece, and I put it here between the two cameras. And then you see that you have 3D data combined from both views. So if you want to see what the contribution of each single camera, you can click on that button. Then it's blue, and then you see only the selected camera. So this is what the Ensensor B contributes. And if I change to the C, then you see what the Ensensor C contributes. And if I click that again, we have the complete view. So that was setting up a multi-camera setup using NXView. And I hope that helped. Check out our other videos on the Vision channel and have a good day. Bye.